The world thinks of Antarctica as a single color, white, infinite, silent, an expanse of snow and broken light where the edges of the planet roll into a blind, frozen horizon. You imagine explorers in parkas, creaking tents, the jagged geometry of ice ridges under a hostile sky. But here's the surprise that doesn't sit well with that neat picture. Beneath that blinding surface, there are places where water refuses to freeze, where lakes lie in secret caverns carved and preserved for millennia, where pressure and geothermal heat and chemistry conspire to keep liquid worlds inside the ice. You and I both grew up with the simple notion that ice equals silence. Yet under kilometers of ice, there are ecosystems and landscapes as alien and as rich as any ocean trench. That contrast, the deafening white above and the humming, liquid dark beneath, is the very hinge of this story. It's where ordinary expectations break and something stubbornly strange begins to whisper. From the first sonar pings that betrayed their presence to the satellite images that mapped a secret geography, these subglacial lakes have been an embarrassment to tidy explanations. They arrived into public view like anomalies in a tidy ledger, unexpected, inconvenient, irresistible. We are promised big revelations about life in extreme environments, about past climates, about how water shapes continents beneath ice, yet every answer births new and deeper questions. Suppose you were told that under 1,000 meters of ice there are lakes that might contain organisms never seen by people, or chemical balances that would rewrite how we think about habitability. Suppose the sediment at the bottom of those lakes holds a record not just of ice ages but of sudden, catastrophic events, of warm intervals that might mirror potential futures. Promise and puzzle sit together here, and that tension is why scientists keep drilling, probing, and arguing. We want to know the truth because the truth is larger than the maps we've drawn. When you look at a satellite photo of Antarctica, it is easy to forget the thickness beneath, ice sheets kilometers deep, dense enough to deform slowly and powerful enough to carve the bedrock. Yet even the most imperious ice must come to terms with gravity, geothermal heat, and the physics of pressure. In certain pockets, a remarkable synthesis occurs. Intense pressure from the overlying ice lowers the freezing point of water. Geothermal heat from the earth below nudges temperatures upward, and chemical salts and gases trapped in sediments change the rules for freezing and buoyancy. Together they create pockets of water that flow and pool and, in some cases, sequester whole micro-worlds isolated for longer than civilization has existed. The early explorers, heroic, often ignorant of the under-ice, only guessed at such things. Modern instruments have filled in the outlines, but instruments are blunt. They tell us that liquid exists and hint at its depth and extent. They do not tell us the stories coiled inside those waters, the slow sedimentation, the microbial dramas, the episodic floods that might link one lake to another like an underground plumbing system. We must tread carefully here, because there is a deep human tendency, especially in stories of dark, hidden worlds, to leap to the sensational. Giants, lost tribes, cursed artifacts. The temptation is seductive. Yet the scientific data is exacting and often stubbornly unromantic. Ice-penetrating radar returns, temperature gradients, isotopic analyses of trapped gases and dust. Still, for all its rigor, science leaves room for wonder because every measurement carries uncertainty. When a radar profile shows a smooth, mirror-like reflectance at the base of a glacier, is that a lake, or something else? Saline slush, a thin film of water, a gas pocket? When a core returns microbial DNA that does not match known sequences, what do we make of it? Contamination, a new branch on life's family tree, or a misread? These are not idle questions but the living texture of the mystery. We are both curious and cautious. We should be both. Picture this. You are at the top of a crevasse field in the long Antarctic twilight. The wind is a constant, oddly tuneless instrument. You feel the weight of icescapes pressing down, and in that moment the idea that something as fluid and alive as a lake could be trapped and hidden beneath you is almost laughable. Yet the science says otherwise. From the lakes first suggested by theorists to the confirmed bodies discovered by radar and then visited, sometimes briefly, sometimes only by the whispering drill holes that lower sensors into an alien dark, the narrative has been one of steady astonishment. Whole networks of lakes, in some regions connected by subglacial rivers that occasionally flush like a clogged artery, move ice and redistribute heat. Here is the astounding part. Changes in those hidden waters can, in time, affect sea level and ice sheet stability in ways our models are only beginning to capture. These lakes are not just curiosities for extreme biologists and glaciologists. They are actors in planetary processes that matter to you, to us, to every coastal city watching the rising tides. But it's not all equations and models. There is a mythic quality to the notion of water hidden under ice. Ancient mariners spin stories about inland seas. Cultures across the world have legends of lakes that swallow whole villages or of underground rivers that carry the dead. In the way we peer into these Antarctic holes, there is a human echo. We are explorers by nature, and the hidden lakes call to that impulse. Picture yourself walking the foggy trail at dawn. I used to say when describing an excavation back in the temperate world, now imagine the fog is not of water but of crystalline air, and the dawn is an instrument tone rising on a spectrogram. The imagination fills in places where instruments only map faint contours. It is not wrong to feel this, but it is also our responsibility to not let narrative outrun evidence. Still, for all that care, allow a whisper of wonder. Beneath that hardness there may be microbial mats glowing in the dark, sluggish currents carrying ancient carbon, an archive of meteor impacts and volcanic tremors buried out of sight. We still don't know how much life, if any, thrives there, and that ignorance is delicious in its possibilities. There have been charged moments when data and myth collided, producing cultural flashpoints. When a radar survey returns the signature of a perfectly smooth basin, people imagine a mirror-like lake with still waters reflecting a starless sky. Others imagine monsters, because humans habitually populate unknowns with animate threats. Scientists, by contrast, imagine conductivity and basal melting and the slow, invisible flow of water that lubricates ice sheets. But both responses speak to the same fundamental human recognition: hidden waters change maps and minds. They make us rewrite our scripts about habitability, resilience, and the deep, hidden processes that shape a planet. That is why, in this story, we will walk through 6 to 8 of the most perplexing and evocative subglacial sites, not as a catalog of coordinates, but as places where history, myth, and data meet and fight and sometimes whisper in harmony. Each of these places tells a slightly different story, about isolation and connection, about the interplay of heat, pressure, and chemistry, about the possibility of life in the margins, and about how a silent lake can become a loud question. Now let's begin the first of those places, a single-sentence teaser that will become a doorway. Deep under the ice, a bowl of liquid holds sediments older than our species, and its chemistry suggests episodic warmth that should not exist. This site was first hinted at by a curious radar return in the late 20th century, when improved satellite coverage and airborne surveys began to reveal black pools at the base of the ice sheet. Teams of geophysicists plotted anomalies and argued about resolution and the possibility of error. By the early years of the 21st century, precise maps began to show outlines, concentric depressions, channels, and possible overflows. The measurements were exact enough to start making claims about scale. Lake basins hundreds of kilometers long, depths measured in tens to hundreds of meters, water under pressure enough to flow despite the 1,000-meter blanket above. We learned about this lake's bedrock geometry, the sediments that hinted at ancient climates, and traces of organic carbon that implied a history of productivity, however limited. We learned dates, layers in the overlying ice that matched particular climatic episodes, volcanic ash layers that tied sediments to known eruptions, and isotopic signatures in trapped gases that pointed to temperature shifts across millennia. These are precise, stubborn facts. Yet they nestle inside questions that refuse to rest. But here's where it gets tricky. The chemistry at the base seemed to imply periodic inflows of warmer water at times when the overlying climate was cold. How could that be? Theories proliferated. One suggested subterranean geothermal upwelling, local hotspots where the crust is thinner, allowing heat to warm basal waters episodically. Another proposed that during ancient interglacials, ice sheet thinning allowed surface meltwater to penetrate and recharge the basins, leaving chemical fingerprints that persisted. A more controversial theory argued for hydrothermal activity linked to tectonic faulting, a hypothesis that would, if true, imply enough energy to create chemical gradients conducive to life in ways we had not imagined for the frozen continent. Each theory had evidence, and each had holes. The geothermal explanation fit heat flow maps but struggled to explain the precise timing recorded in sediment layers. The surface refill hypothesis matched climate records but could not easily account for certain isotopic ratios. Now, let's be fair, this is where method matters. Careful coring and repeated measurements winnow out the least plausible ideas. Still, for all the evidence, the pattern of episodic warmth remains an open riddle. Imagine standing at the lip of this basin in a thought experiment. The air is thin and cold in your breath clouds, but below your boots the ice is a roof to a dark lake that has seen epochs pass like unread pages. Imagine lowering a camera on a fiber optic cable and watching its light scatter across black waters where particles drift in slow majestic swirls. Picture the sediment core pulled up like a time capsule, dark, fine-grained, interleaved with layers of ash and pollen and microfossils that don't match any modern analog. Picture the argument among researchers as they stand over the core, one saying, "Volcanic signal," another saying, "Evidence of past surface melt," a third whispering, half in jest, about ancient voyagers who might have navigated a warmer Antarctic when sea levels were different. It is easy and perhaps irresponsible to let myth overtake method. Yet even a reflective insight here is rich. When faced with such deep, cold enigmas, our old stories of lost tribes and giants are not literal claims but symbolic attempts to account for the scale of time and the depth of isolation. We still don't know whether life once flourished in this basin or whether its chemical secrets are merely geological decorations on a barren stage. The story that unfolds at this first sight is emblematic. It shows how careful measurement collides with human imagination, how isotopes and legend both seek to explain the inexplicable. We will find similar patterns in the other basins: precise, stubborn data, competing theories, and a bristling edge of the mythic. Each site will invite you, and force us, to picture the scene, to imagine walking a foggy trail at dawn, albeit a trail of instruments and cutting-edge drills rather than footprints. The emotional payoff is slow but real. These are places where science humbles itself, and where wonder becomes an appropriate companion to skepticism. As you listen, remember that the deeper we dig, the more the planet seems to conceal entire worlds under what we once thought was simple and empty snow. We still don't know how many of those worlds are alive. Deep under the East Antarctic Plateau there is a ribbon of liquid that looks less like a single pond and more like an underground river, a discovery first hinted at by airborne radar surveys in the 1990s and then more carefully mapped by teams working through the 2000s, and its existence hints at an invisible plumbing system that connects lakes across hundreds of kilometers and might, in the right conditions, move ice like gears in a machine. The teaser is simple. Imagine a river running where no river ought to be, sliding beneath a continent of ice and changing the way glaciers breathe. To understand its scale, picture measurements taken from ice-penetrating radar showing channels tens to hundreds of meters wide, nodding into basins that stretch across the scale of small countries. Think of flow rates estimated in cubic meters per second when a lake drains, and the slow, persistent lubrication produced at the base of a moving ice sheet. Historically, the seeds of this discovery can be traced to a burst of Antarctic science that followed the International Geophysical Year of 1957-58, when nations agreed to mount a systematic study of the polar regions. From those early expeditions, it took decades of technological refinement, better radar, improved gravity surveys, satellite altimetry, to reveal a network of dark reflections and subtle depressions suggesting conduits of water. By the early 21st century, mapped features in this region had been characterized down to coordinates, depth approximations, and flow directions, channels linking subglacial basins across transverse valleys, sometimes dipping and rising in ways that made them look eerily like subterranean rivers carved by a long-forgotten hydrology. Key discoveries at this site are the marriage of movement and storage. Scientists observed periodic events where one lake would abruptly lose volume, while a downstream basin swelled, a hidden flood that traveled beneath the ice with the velocity of a slow river surge. Core samples pulled from adjacent sites showed layering that suggested episodic scouring and redeposition of sediments, and isotopic signatures in the trapped gases hinted at pulses of change rather than gradual, indifferent accumulation. Seismic surveys painted a picture of variable basal roughness, patches of smooth, water-lain bed and patches of sticky, sediment-choked ridges. Together these data imply that the plumbing is dynamic, canals open and close, sometimes shunting water downstream in dramatic flushes. Socially and culturally, the research community grouped into competing camps. One set of glaciologists argued that these conduits are mostly passive, responding to surface melt pulses that puncture down through crevasses and moulins in times of warmth. Another argued that internal geothermal gradients and pressure-driven flows play a larger role, creating self-sustaining channels that can evolve independently of surface conditions. There was also a provocative third view that these channels are the slow nervous system of the ice sheet itself, a physically emergent network helping the ice adjust to stresses and redistributing loads across vast distances. But here's where it gets tricky. The dynamics of this plumbing have implications that reach far beyond Antarctic curiosity. If a subglacial channel system can convey large amounts of water quickly from interior basins to the continental edge, it could change how ice flows into the ocean, and thus how fast sea level rises. Some models show that rapid drainage events increase basal lubrication and could transiently accelerate glacial flow. Others contend that once the system is established, it stabilizes. A persistent channel efficiently evacuates water, preventing the kind of chaotic pooling that leads to major surges. The competing theories are grounded in different combinations of data. High-resolution radar gives a static map, seismic and tremor data hint at movement, and satellite altimetry suggests volume changes over time. Each line of evidence tells a partial truth, and when combined they make a picture that is complex and not yet decisive. Now, let's be fair. The uncertainty is not ignorance so much as the natural state of a system that responds to rare, high-energy events interspersed with age-long slowness. Still, for all the evidence, we cannot predict when a particular channel will flush next, how large it will be, or whether an interconnected system can produce cascading failures that matter at continental scales. Imagine yourself placed in a thought experiment on the ice above such a channel. You stand by a crevasse rim at dawn, wind pushing cold along your face, the landscape a muted cathedral of broken light, and you feel utterly alone until you realize the ice beneath you hides motion as deliberate as a heartbeat. Picture lowering an instrument into a borehole and feeling a tiny vibration as the water passes. The instrument sings back with a frequency that, after analysis, reads like the rhythm of an unseen, underwater flood. Consider the sediment core brought up from a nearby basin, fine laminations interrupted by coarser layers that read as the fingerprints of hurried flow. Picture the debate in the control tent where maps are spread, one researcher tracing a line of channels and predicting a surge, another cautioning that the data could be explained by local meltwater pulses during a warm interlude thousands of years ago. The mythic overlay is easy to conjure. Tunnels like secret veins carrying the continent's lifeblood, subterranean arteries that once, in the language of sailors and storytellers, might have routed dragons or giants across hidden waterways. And yet even the myth is an attempt to grasp scale and mystery. The reflective insight is that the continent, which seems immutable and absolute, is in truth porous and patient. It buffers and redistributes change in ways that our surface-centric sensibilities do not immediately register. We still don't know whether these hidden plumbing systems will act as buffers against change or as triggers for sudden, large-scale reorganization. Turn next to a different enigma. A deep, mirror-smooth basin isolated beneath the West Antarctic ice sheet whose chemical profile suggests a cocktail of salts and gases that could host unusual metabolisms, hinting at life that would rewrite our definitions of habitability. The one-sentence teaser. This lake's water chemistry looks less like ordinary fresh water and more like the strange, briny solutions we expect in alien seas. Historically, the West Antarctic region has been the subject of intense study, particularly since mid-20th century expeditions established research stations and later, airborne campaigns plotted the basal topography. Measurements at this basin reveal salinity gradients and unusual concentrations of dissolved gases, methane and sulfide in proportions that do not match simple models of trapped ancient seawater or straightforward chemical weathering. Radiometric dating of entrained sediments suggests that parts of the basin were isolated tens to hundreds of thousands of years ago, perhaps capturing a snapshot of ancient marine intrusions or episodic geothermal activity. The scale is forbidding. This basin is, by some estimates, hundreds of square kilometers in area and tens to hundreds of meters deep, with layers of chemical stratification that could create microhabitats, each with its own redox chemistry and potential for unique metabolic pathways. Key discoveries include traces of organic molecules in the sediments that are structurally distinct from typical terrestrial biomarkers, and microfossil-like structures that under higher resolution imaging resist easy classification. There are also telltale mineral deposits along the basin margins, sulfur-rich mats and iron-rich laminae, that hint at chemosynthetic processes capable of converting inorganic energy into biological biomass. The competing theories are instructive and imaginative. One mainstream explanation is that ancient marine water intruded into this subglacial basin during a period when sea level and ice extent permitted such exchanges, bringing with it salts and marine microorganisms that later adapted to the closed, cold conditions. Another theory posits active hydrothermal vents at the base, where geothermal energy drives chemical gradients that chemosynthetic life can exploit, akin to life around deep-sea vents in the global ocean. Yet another suggestion, more speculative and less accepted, imagines a long-term, slow chemical evolution within the sealed basin producing novel metabolisms from peculiar starting conditions. Each theory leans on different strands of evidence. Mineralogy favors geothermally influenced environments. Certain organic signatures align with marine input, and the stratigraphy suggests varying histories that could include both processes at different times. Now, let's be fair. Contamination is a perpetual worry, and the scientific community has been meticulous in demanding clean protocols for any sample that could bear life's signatures. Still, for all the checks, the chemical story resists a tidy single-cause explanation. Picture yourself in that moment before a sterile coring operation. The tent hums with generators. Scientists in bright parkas prepare a drill that will cut a sterile path through kilometers of ice, and everyone knows the one rule above all: no contamination. Picture the scene as the drill breaks through and a window to a liquid, briny world opens. For a moment, to the light, a sliver of black that vanishes as the drill seals again. Picture the samples hauled up, dark, compacted sediments that carry bubbles of ancient gases, and a lab team whispering over microscopy images that show structures neither clearly biological nor purely mineral. Hear the mythic register step in, voices imagining ancient seakeepers, or salt giants, who once moved in waters that are now trapped under ice, images drawn from folklore turned into metaphor for the scale and strangeness of what lies beneath. The reflective insight here is ethical as much as epistemic. If life exists in such pockets, how should we act? Do we have the moral right to stir those waters? Our curiosity is a hammer, but in these rooms we are learning to wield it with a surgeon's care. We still don't know whether these chemical pockets host living ecosystems, dormant life, or merely the ghost chemistry of a planet's long memories. We still don't know. We still don't know. Beneath the ice, the questions stack like strata. Each layer of evidence brings another riddle, and each riddle invites us to imagine more. Consider a basin that reads like a palimpsest of cataclysm, a site where sediment cores whisper of sudden, violent events separated by long silences, where the chemistry and grain sizes suggest not only slow accumulation but episodic scours that reshape the floor in geologic heartbeats. The teaser for this place is blunt. The lake bottom records abrupt upheavals that some teams read as cometary impacts, while others point to subglacial volcanic pulses or catastrophic meltouts. The history of discovery here is a study in patient refinement. Early radar surveys identified a smooth depression, later seismic campaigns detected chaotic layering beneath, and then long, painstaking coring pulled up tapestries of ash, microspherules, and breakable laminations that could be read, if one were careful, like chapters of a long-forgotten and partly burned book. Radiocarbon and other chronometers, teetering at the limits because of age and contamination concerns, gave anchors to a chronology, pulses around tens of thousands and hundreds of thousands of years ago, mineral fingerprints that sometimes aligned with known global events and sometimes with nothing we have yet matched. Key discoveries at this site are the mismatch between the apparent violence recorded in sediments and the slow, glacially mediated surface conditions one would expect. There are layers punctuated by coarse, angular grains that could only have been delivered by energetic flows. There are tiny glassy spheres, microspherules, whose shapes suggest melting in an instant at extremely high temperature, the sort you might associate with an extraterrestrial body striking the planet or a rapid, explosive volcanic event. There are, alongside these markers, geochemical anomalies, spikes in iridium in places where terrestrial sources are unlikely, sudden pulses of exotic isotopes that do not match the steady-state weathering profiles we see elsewhere. From these data, hypotheses proliferate like footnotes to a controversial book. One camp suggests that during certain windows the Antarctic surface was stripped or thinned just enough for atmospheric impacts to penetrate and melt localized areas, injecting heat and material into subglacial basins. Another counters that deep crustal magma movements could have produced hydrovolcanic explosions beneath the ice, blasting glassy spherules and ash into the water and rearranging sediments in a single, violent episode. A third, more conservative set of voices proposes that the signatures are the product of high-energy ice stream surges, where mechanical abrasion and rock-on-rock grinding could simulate some of the physical proxies of impact events without the need for an outsider visitor from space. But here's where it gets tricky. Each interpretation carries vast implications. If impactors, comets or asteroids, have made it through the thick, protecting shroud of ice on multiple occasions and left signatures in the subglacial record, then Antarctica becomes a crucial archive for planetary bombardment histories that we currently reconstruct mostly from oceans and terrestrial outcrops. If hydrovolcanism is the leading explanation, then we must accept a more dynamic Antarctic crust, with heat pulses capable of altering basins and perhaps creating transient refugia for life. If mechanical surges explain the evidence, then the ice sheet's internal dynamics are more violent and episodic than many models allow. The evidence itself is maddeningly equivocal. Microspherules can be produced by many processes. Iridium anomalies are powerful hints but can be concentrated by local geology. And seismic signals leave more questions than answers when read at tens of kilometers of distance. Now, let's be fair, rigorous interdisciplinary work, combining microscale sedimentology, isotope geochemistry, and high-resolution geophysics, is slowly triangulating the likeliest scenarios, but none of them yet fits every stripe of data. Still, for all the evidence, the question of what punched and scoured and then silenced this basin remains open. Picture yourself as the person whose hands part the thin wrapper of a sediment core and reveal the cross-section of millennia, bands like tree rings but far more complicated, some a whispered fine dust, others a coarse mosaic of fractured minerals, and every so often a dark, glassy seam that catches the light and looks like the memory of fire. Imagine the room where the core goes under the microscope, the hum of refrigeration, the shuffling of gloved hands, a lab member calling out peaks on a mass spectrometer, as if reading a musical score. Picture the argument that follows, respectful but heated. One scientist points to microtextures that only form under megabar pressures, another to the temperature-dependent rounding of glass spheres, yet another pulls up analogs from deep-sea drill cores and finds both similarities and glaring mismatches. The mythic overlay is inevitable and irresistible, narratives of celestial stones sliding through silence, of a world punctured by the cosmos, or of ancient skyfires carving scars that later cultures might have memorized as myth. Even as the scientists parse textures and ratios, the cultural imagination stitches these signals into larger stories about cosmic vulnerability and Earth's punctuated past. The reflective insight here is sobering. Our planet is not merely a backdrop but an arena where internal and external forces meet, and the icy continents are archives of both, records kept in the language of glass and grain, waiting for us to learn their dialects. Turn your mind now to another enigmatic subglacial environment, a network of shallow pockets along a tectonic boundary where the bedrock itself seems to be a character in the story, folding and breaking in ways that feed chemicals into the lakes and perhaps even provide habitats in places where sunlight and warmth are absent. The teaser is lyrical. Bedrock fractures breathe life into the dark, offering chemical scraps that hungry microbes could feast upon. The stakes here are geological and biological. frictional heating along faults, serpentinization reactions where mantle rocks interact with infiltrating water, and the steady production of hydrogen and methane that can sustain chemosynthetic ecosystems in total darkness. Historically, this theory rose from the combination of regional geology, knowledge of rift zones and ancient crustal weaknesses, and geochemical anomalies measured in basal waters. Gravity surveys showed variations that hinted at denser material and structural complexities. Magnetics suggested ancient crustal boundaries, and small, local tremors recorded by seismometers hinted at an active, if sluggish, tectonic life beneath the ice. Taken together, these lines of evidence suggested that the subglacial environment was not merely passive but chemically productive in places where rocks meet water under pressure. Key discoveries here are the detection of reduced gases in water samples and the presence of minerals that form in the wake of water-rock reactions known to produce biologically useful energy fluxes. Sediments contain mineral assemblages that point to the exposure of ultramafic rocks to aqueous alteration, a chemical alchemy that yields hydrogen, a currency for life. Competing theories split mainly on the rate and distribution of such reactions. One model argues for scattered hotspots where tectonic strain and fault-driven fluid flow produce localized, biologically rich oases. Another envisions a more extensive crustal process that supplies a background flux capable of sustaining low-density, widespread microbial communities. Yet another hypothesis suggests that such chemical food chains have, in some basal basins, been active long enough to fuel evolutionary innovation, producing metabolisms that differ markedly from the surface-dominated biology we study on continents and in oceans. Now, let's be fair, proving life here, and its degree of novelty, is enormously hard. Samples risk contamination, energy fluxes may be marginal, and the time scales involved could be glacially long. Still, for all the evidence, the possibility that bedrock chemistry fuels life under kilometers of ice remains one of the most enticing scientific prospects. Imagine walking on an ice plain above such a geological seam and feeling the almost imperceptible rumble of crustal breath. Picture a borehole team lowering a sampler and then, hours later, watching a cloudy vial come up carrying dissolved gases and particles that test as chemically exotic. Picture the lab where technicians run reactions and find the signature of hydrogen production consistent with serpentinization. Picture a scientist pausing, then whispering, because the ratios she sees in the gas sample are ones that, on other worlds, have been associated with life. The mythic overlay is again vivid. Out of the hard, mineral world comes a kind of sustenance, the rock giving in to water like a parent sharing its store. And the idea that life could persist in such inhospitable places resonates with ancient stories of underground hearths and hidden springs that keep villages alive in winter. The reflective insight is tender. Life, if present, would not be a spectacle but a stubborn, patient presence, eking out a living where light never falls. It would be a reminder that where there is a gradient, chemical, thermal, mechanical, life often finds a way to march. We still don't know whether these rock-fed habitats are abundant or rare, whether they host lineages we've seen before or ones that would force us to redraw the tree of life. We still don't know. Yet even in uncertainty, the lake basins and channels and chemically rich pockets teach a lesson about how science moves forward, not as a straight arrow from ignorance to knowledge but as a messy, iterative conversation in which measurements and myths trade places, challenge each other, and refine the questions. Picture the larger tapestry, impact signatures and volcanic pulses, hidden rivers and chemical oases, all stitched beneath the white, each thread offering potential insights into planetary processes, climate history, and the limits of life. Picture us, not as conquerors of the unknown, but as listeners, trained and impatient, who approach the ice with instruments and stories, with protocols and poems, hoping to coax out narratives that are both precise and human. The reflective truth is that Antarctic darkness is not merely absence but a concentrated archive. Whether we read it correctly will depend on our humility, our method, and our willingness to let wonder sit beside skepticism as equal partners. We still don't know how many secrets lie under the kilometers of ice, but we do know that every core, every radar sweep, and every carefully filtered sample brings us a little closer to understanding the deep, cool heart of our planet. Beneath the Russian polar station, a century of human ambition met a slab of silence, and in 2012, a drill finally punched through to a world that had been sealed for millions of years. A lake that had slept under ice for epochs, and whose first taste of human light sent ripples through both labs and imaginations. The teaser here is intimate and unsettling. A sealed lake opened at last, and in its dark waters were hints of life that did not fit neatly into the tree we keep for living things. To set the context, remember how polar science matured, from the International Geophysical Year of 1957 to 58, and the heroic bases that followed, to decades of airborne radar surveys, to specialized drilling programs in the late 20th and early 21st centuries aimed at sampling the basal environment without destroying it. When the drill finally found the liquid, the world held its breath. The measurements that followed were cautious: filtered samples, multiple contamination controls, independent labs, and yet what arrived at microscopes and sequencers seemed to promise something more than geology. There were odd sequences of DNA, fragments that matched known microbial groups in part but diverged in ways that made taxonomists frown and wonder whether what they were seeing was contamination, a long-evolved island of microbes, or the residue of chemical life whose traces had shifted so far from known relatives that classification strained at its edges. Key discoveries in that event were both practical and philosophical. Practically, the demonstration that a sterile protocol could reach a subglacial lake and return analyzable material was a milestone. Philosophically, the suggestion that life could persist, perhaps even diversify, in total darkness under immense pressure overturned comfortable limits. Researchers measured chemical gradients in the water: low oxygen, pockets of methane, traces of sulfate reduction, and they found sediment particles carrying organic carbon in forms that required explanation. Competing interpretations emerged, as is the nature of science. One conservative view cautioned that any biological signatures could be the ghosts of contamination introduced during drilling. DNA is stubborn, and even the cleanest systems can betray us. Another posited that the signals were genuine and represented extremophiles adapted to chemosynthetic lifestyles, feeding on mineral-derived energy rather than sunlight. A more imaginative but cautiously voiced hypothesis suggested that such isolated lakes might be evolutionary cradles, places where microbial lineages evolved along separate branches for millions of years, producing metabolisms and morphologies unfamiliar to surface life. Each position leaned on different evidence. Contamination proponents pointed to possible drilling fluid residues and minor matches to common lab strains. Believers in endemic life emphasized unique isotopic signatures and unusual lipid biomarkers. Evolutionary optimists pointed to the isolation timescales, measured in hundreds of thousands to millions of years, as ample opportunity for divergence. But here's where it gets tricky: the implications are more than academic. If life, even microbial life, can persist and perhaps diversify in such sealed dark basins, then our understanding of habitability must broaden. The very definition of an environment that can nurture life shifts from the sunlit surface to include chemically driven, pressurized, and chronically cold niches. That bears directly on astrobiology. Moons like Europa and Enceladus, with their ice shelves and subsurface oceans, move from speculative to plausible when we can point to terrestrial analogs. Yet the stakes also turn ethical. How do we balance the hunger for discovery against the duty not to irreversibly alter an ecosystem that evolved in isolation? The protocols developed: multi-barrier sterilization, redundant sampling, cautious interpretation, are not mere bureaucratic steps but moral scaffolding erected because the consequences of contamination could be global for science. Imagine, for instance, a mislabeled DNA sequence from a drill rig becoming the line that defined an entire new branch of life, only to be later exposed as a human artifact. The community would suffer a scandal less about error than about how easily hope colludes with haste. Still, for all the precautions and debates, the deeper, persistent truth remains: the subglacial world open to humanity in that moment had the potential to rewrite natural history, and we are still only beginning to read its pages. We still don't know. There are water worlds, and there are borders where water meets ocean in a clash that both erodes and sustains. Along the frozen fringes where ice shelves meet the sea, cavities under floating shelves hide currents that flow in from the ocean, carrying warmth that melts undersides and reshapes the grounding line. The teaser is urgent: Warm ocean water sneaks beneath ice shelves and undermines the continent from the margins inward. To appreciate the consequence, chart the modern history. Since the late 20th century, as satellite altimetry and submersible surveys matured, scientists found that certain ice shelves, once thought stable and eternal, were thinning from below. The measurements were precise enough to show seasonal and secular trends, melting rates that accelerated when circumpolar currents or shifting wind patterns delivered warmer water onto continental shelves. The sites in question are not remote curiosities but the front line of potential sea level change. They are where oceanography and glaciology meet, where a subtle increase in subsurface ocean temperature can translate to meters of ice loss over decades. Key discoveries at these margins revealed that channels and cavities under shelves are dynamic. Warm water can penetrate through submarine troughs, pool and grounding zone cavities, and create meltwater plumes that force the cavity upward, carving channels and weakening ice from below. Observations from autonomous underwater vehicles and hot water-drilled access holes documented scalloped ice undersides, plumes of buoyant fresh water laden with sediment, and melt rates that rose in lockstep with shifts in ocean heat. Competing theories about drivers divided around large-scale climate patterns and local topographic controls. Some researchers argued that large-scale atmospheric changes, shifts in wind stress associated with modes like the southern annular mode, altered upwelling and currents, steering warm water into previously safe bays. Others stressed the importance of bathymetry. Deep troughs carved by past glaciers act as conduits, letting relatively warm, deep ocean water reach the ice shelf base where it can do the most damage. A third, integrative view suggested that feedbacks between ice shelf thinning and ocean circulation create self-reinforcing dynamics. Once a shelf thins enough to expose more ocean surface to wind-driven mixing, the local circulation changes in ways that favor further warming and melt. But here's where it gets tricky. The hidden cavities are not merely passive recipients of ocean heat. They harbor ecosystems and chemistries that respond to change. Meltwater plumes deliver nutrients, reshape salinity gradients, and can flush sediments accumulated under the shelf into the open ocean, carrying a record of past climates and possibly of life adapted to the sub-ice environment. There are suggestions, tantalizing but not definitive, that microbes living at the ice-ocean interface can metabolize in ways that influence local biogeochemistry, perhaps producing methane or other gases that then bubble into the water column. The mythic overlay is dramatic. Imagine tides carrying warmth like a living hand under the ice, eroding anchors that have held the continent in place for millennia. Picture sailors' legends of sea spirits undermining cliffs. Here, a modern echo, with physics in the role of myth. The reflective insight is urgent. These margins are where we might see the fastest consequences of anthropogenic climate change, yet they are places of genuine scientific surprise because the ocean's deep heat can do what surface temperature alone cannot. We still don't know how these sub-ice ocean interactions will play out decades hence, whether they will unfold as slow, predictable retreats or as abrupt reorganizations that surprise our best models. Closer to the center of the ice, in places where vast cold domes and storm-bent ridges create resonant cavities, instruments have detected a kind of subterranean music, acoustic signatures, long-period tremors, and spectral harmonics that refuse simple explanation. The teaser here is eerie. The ice sings, and its song changes when the hidden waters move. Historically, the study of ice sounds is new. The first borehole seismometers and acoustic arrays were deployed in the late 20th and early 21st centuries, and they revealed that glaciers are not silent. There are creakings, snaps, and the long hum of slow flow. Some signals look like the groaning of a ship's hull under stress, others like the hiss of water moving through rock. The recorded spectrograms show sustained frequencies that sometimes cluster around events of subglacial flooding or basal slip, and other times occur without any obvious surface correlate. Key discoveries in this acoustic realm include correlations between certain long-period tremors and rapid drainage events recorded by satellite altimetry. When a lake drains beneath a glacier, the sudden redistribution of mass creates seismic signals and a chorus of low-frequency noise. Yet not all recorded signals line up with visible mass changes. There are harmonics that persist for weeks, and occasional sharp tones that suggest resonant cavities filling and draining slowly. Competing theories attempt to map these sounds onto physical processes. One explanation ties them to hydrofracture, the propagation of water-filled cracks that make resonant tones as they open and seal. Another links them to turbulent flow in subglacial channels, where eddies and shear produce tonal features in acoustic records. A more speculative idea suggests that chemical reactions at the ice-bed interface, gas release, bubble formation, clathrate transitions, could produce sounds as gases nucleate and escape under pressure. Now, let's be fair, seismology is an inverse problem. Many models can be fit to a given set of observations and only rigorous, multimodal campaigns can favor one over another. Still, the idea that the ice itself is a sensor, its song carrying the signature of mechanical and hydrological processes, is a profound shift in how we might monitor concealed systems. Imagine standing in a tented camp where technicians listen to a live feed and translate it into images. The room can feel like a cathedral where every hum and thump becomes a note in a subterranean symphony. Picture lowering mics into boreholes and hearing a roar that, when plotted, looks like the sound of a distant storm although the surface is calm, or hearing a thin, repeated ping that aligns with the pulse of meltwater recorded hours later by satellite. The mythic overlay is cinematic. Ancient myths often personify nature's sounds as voices, mountains that speak, seas that sigh, and the singing ice invites the same imagination. The reflective insight here is methodological. If we learn to read the music of ice, we gain a tool for monitoring inaccessible dynamics in real time, a way to hear change before it becomes visible. We still don't know the full orchestra of sounds and their precise physical correspondences, nor whether new, unheard signatures will emerge as climates and circulations shift. There are places where the sediments at the bottom of subglacial lakes capture pollen, dust, and chemical signals that read like a climate diary, pages that narrate not only Antarctic conditions but global connections, dust from deserts transported in the atmosphere, ash from distant volcanoes, microfossils from distant seas, and abrupt chemical shifts tied to planetary scale events. The teaser here is archival. These basins are libraries written in clay and carbon, and some volumes have remained unread for hundreds of thousands of years. To understand the weight of this archive, recall how paleoclimatology has used ice cores and marine sediments as proxies. Subglacial basins add a new, complementary archive, sedimentation that is protected from surface reworking and that can, in some basins, preserve very high-resolution records of abrupt events. The measurements that come from careful coring, grain size distributions, tephra layers dated by known eruptions, isotopic excursions, allow correlation with other global records, providing a fuller picture of how Antarctica has participated in, and responded to, planetary shifts. Key discoveries from these cores include surprising synchronicities, layers that match volcanic eruptions known from other hemispheres, dust peaks that align with aridification events in distant continents, and episodes of increased organic deposition that may mark times when meltwater pulses carried nutrients and biomass into the basins. Competing theories again navigate interpretation. Does a spike in certain isotopes reflect a local process, like venting of hydrothermal fluids, or a distant one, like stratospheric ash fallout from a massive eruption? If we find microfossils that appear to be marine in origin, were they deposited during a time when the continent's margins were open and seas invaded, or transported through complex hydrological connections? Some scientists argue for careful, multi-proxy triangulation, using magnetostratigraphy, tephrochronology, and isotope systems together, to build robust chronologies. Others warn that the closed nature of basins and the potential for in-situ chemical alteration can mislead if we rely on single-line evidence. The mythic overlay is historiographic. These sediments are time capsules, and the temptation to read them as prophetic texts is strong. The reflective insight is humbling. Each core is a dialogue between past events and present interpretation, and our scientific honesty demands patience, replication, and a resistance to narratives that fit neatly but are poorly substantiated. We still don't know the full story written in those clays, nor how many missing chapters remain buried and unread. We still don't know. Across these sites the refrain returns like a drumbeat, evidence accumulates, theories multiply, methods refine, and wonder persists. Each lake and channel and cavity we study complicates the map and broadens the question set. There are places where chemical gradients suggest life, where sedimentary textures hint at cosmic arrivals, where water under pressure moves like a quiet animal, and where the ice sings of events we cannot yet fully diagnose. Taken together, these mysteries do something important. They force us to accept complexity as the norm rather than the exception. They teach humility because the planet keeps secrets with patience and because our models, however elegant, are only as good as the data and the interpretations we permit ourselves to challenge. Imagine yourself years from now, not as a distant, satisfied reader but as an active participant in a field that learned, finally, how to balance curiosity with care. Picture a team in a lab, decades of protocols in a binder, arguing about a sequence that refuses classification. Picture an autonomous vehicle gliding through a sub-ice cavity and transmitting imagery of an underwater ridge that no radar had resolved. Picture a network of acoustic sensors that, when stitched together, let us listen to the continent and anticipate sudden drainage events. Picture the ethical frameworks that will have matured in parallel, agreements about sample sharing, contamination mitigation, and even the right of an environment to remain unprobed. All these are not dreams but plausible outcomes if we proceed with intelligence and restraint. And there is a deeper, more human payoff. As we learn these hidden geographies, we grow in our capacity to hold wonder and doubt together. Now, let us be clear about the stakes. What happens beneath the ice does not stay beneath the ice. Changes in basal hydrology can alter ice dynamics and, by extension, influence global sea level. Chemical and biological discoveries can reshape our notions of habitability and guide the search for life beyond Earth. Sedimentary archives can refine models of climate sensitivity and feedbacks. Acoustic monitoring can provide early warning systems for rapid changes. These are practical concerns with existential dimensions. They shape how coastal cities plan for the future, how astrobiologists prioritize missions, how policymakers weigh conservation against exploration. The myths, giants drifting in hidden waters, lost tribes frozen in time, skystones punching through the ice, while not literal, perform a useful cultural role. They help communities relate to abstract processes, to visualize scale, and to emotionally process change. But myths are not substitutes for science. They are the language of feeling layered atop the grammar of measurement. If I could close with one image, it would be this. You stand at the edge of a crevasse field at the polar dawn, breathing cold, watching the first hesitant light paint the snow a pale, metallic rose. And you know two things simultaneously: that the surface before you is an ocean of white, and that beneath it, entire worlds are folded and preserved like secrets in a book whose pages we are only now learning to turn. That double awareness, of surface simplicity and subterranean complexity, is the abiding lesson of these hidden lakes. Keep digging, some secrets still lie just beneath your feet. If all of the threads we have followed across ice and time are woven together, a picture emerges that is neither tidy nor hopelessly obscure but instead insistently human. Antarctica's hidden lakes are both mirrors and mirrors of mirrors, reflecting something of our planet and reflecting back our deepest questions about life, change, and responsibility. Across basins and channels, in acoustic signatures and glassy spherules, in briny chemistries and rock-fed hydrogen, we have seen the same dialectic again and again. The Earth writes with precision, and we answer with stories. Those stories are scientific: isotopes, radiometric anchors, radar profiles, sedimentary laminations, and they are cultural: myths of subterranean seas, metaphors of veins and arteries, ancient imaginings of fire and cold. The two kinds of narration enrich one another when we are careful. Myth gives scale and feeling to the cold arithmetic of data, and data tethers myth to reality so that wonder does not become credulity. The emotional payoff of this work is not a single discovery but the transformation that comes from learning how to listen, how to slow down, and how to let humility temper ambition. Each lake we touch, each channel we map, each core we slice open, insists, sometimes with the clarity of a measured ratio and sometimes with the softness of a poetic image, that our planet is a complex interlocutor, and that our proper role is to be students rather than heirs of certainty. Think of the practical lessons etched into this continent's under-ice archive. Hydrology under the ice is not a tidy plumbing diagram but a dynamic and sometimes furious circulatory system. Lakes that accumulate quietly and then drain in pulses, channels that open and close, cavities that funnel warm water to points of weakness. The physical consequences are clear and consequential. Basal water changes can modify the sliding behavior of ice, shifting how stress is transmitted across an ice sheet and ultimately changing the rate at which ice reaches the ocean. That connection between hidden water and visible ice flow is not abstract. It has direct implications for coastal communities around the world and for the models we rely on to predict future sea level rise. Similarly, the chemistry sequestered in those basins, the salts and gases and mineral assemblages that do not fit into our neat categories, challenges our definitions of habitable environments, and informs the search for life beyond Earth. If a briny subglacial lake sequesters a chemosynthetic community, or if rock-driven serpentinization fuels an under-ice ecosystem, then moons and icy planets with subsurface oceans do not seem like far-off fantasies but rather possible extensions of what life can exploit. And if sediments that preserve the fingerprints of impacts, eruptions, or abrupt melt events, those pages of the Earth's memory become central chapters in the planetary story that we are still piecing together. Yet the lesson is not only in the instrumental or the theoretical, it is also ethical and procedural. Humanity's first contact with these sealed places has been cautious because we learned quickly that curiosity can be destructive. The protocols that have developed, sterilized drills, multi-layer sampling, the ethic of leaving some places unprobed, are not merely conservative bureaucratic apparatuses but evolved safeguards born from the awareness that contamination would be both a scientific and moral catastrophe. Consider the scenario of a mislabeled DNA fragment introduced by a drill contaminant and later mistaken for an endemic lineage. Such an error would be more than embarrassment. It would rewrite scientific narratives on a foundation of human artifice. Conversely, the decision to leave some lakes unvisited, to let parts of the planet remain pristine archives, is not scientific cowardice but an exercise in restraint that recognizes that knowledge sometimes exacts a cost. The mature posture, which is beginning to take hold in polar science, is one of reciprocal respect between investigator and subject, a recognition that the continent guards its records jealously and that we must ask the right questions in the right way, with protocols that preserve the ability of the planet to remain itself even after we have looked. There is also a communal and cultural dimension to this work. The public imagination is not an adversary of careful science, it is an ally that brings attention, empathy, and political will. But that attention must be guided by clear communication and humility. The myths that arise around subglacial lakes, giants, lost tribes, skystones, are not necessarily illusions to be dismissed. They are the human mind's attempt to narrate enormity. Our task as scientists and storytellers is to translate the precision of isotopes and radar into language that retains wonder but refuses deception. We gain nothing from rendering science as mere spectacle, yet we lose much if we sanitize it into arid paragraphs devoid of feeling. The best narratives marry the two, they present the stakes, climate, habitability, deep history, honestly, and then allow the imagination to inhabit the spaces the data leave open. In doing so, we cultivate a public that is informed and moved, capable of supporting the long-term projects, funding monitoring arrays, protecting research protocols, sustaining international cooperation that this field requires. As for the speculative honors that science sometimes receives, the grand proclamations about life, the dramatic claims of immediate planetary consequences, those are tempered by the slow, iterative process that real knowledge requires. When we say, "We still don't know," it is not an admission of failure but a commitment to the work of triangulation, to repeat measurements, to cross-validate proxies, to let alternative hypotheses compete and to let the most robust survive. Science advances not by aggrandizing the uncertain but by converting the uncertain into a lattice of well-tested inferences. Over time, we should expect many of the contentious questions to be settled. Some basins will prove sterile, others will harbor microbes constrained to chemical niches, some signatures now read as possible impacts will be traced to local volcanic episodes, and some acoustic harmonics will be matched to specific hydrologic mechanics. But even as these answers accumulate, new questions will arise, finer, harder, and often more profound, because complexity breeds curiosity. The emotional core of this work is patient awe. There is something quietly profound about realizing that beneath the remorseless whiteness that covers our maps lies an archive of time longer than human memory, and that within that archive are processes and possibilities that make us feel both small and capable. Small, because in geological terms our species is an eye blink. Capable, because we have developed instruments and social norms that allow us to access, interpret, and protect these places responsibly. The reflective insight here is not sentimentality but a kind of ethical optimism. The very fact that we can follow questions with care suggests that humans can be stewards of discovery, not merely exploiters. That stewardship must be global, because Antarctica is a planetary commons. Its hidden lakes are not the province of a single nation or a single lab but a shared heritage whose value is intellectual, moral, and practical. There will be hard decisions ahead. Funding is finite, and choices must be made about which basins to probe, which to monitor remotely, and which to leave untouched. Models will fail and need revision. Policies will lag behind findings and must be pushed forward by scientists and citizens alike. But the arc of this research also offers clear pathways: improved, cleaner sampling technologies, denser acoustic and radar monitoring networks that reduce the need for intrusive drilling, more international coordination around access and data sharing, and robust public outreach that makes the stakes clear without feeding sensationalism. The long view is hopeful because the scientific community, by its nature, responds to new knowledge with new safeguards and new creativity. What once was done in isolated tents and with casual sterilization is now a field of carefully codified methods and shared norms. That maturation matters as much as any single discovery. And finally, there is the human, narrative closure that every good story requires without betraying the scientific need for openness. These lakes, channels, and cavities are not merely geological curiosities. They are testimonies to time, to resilience, and to the interplay of fragility and endurance. They remind us that Earth is full of hidden places that matter to the whole system and that our duty as observers is twofold: to learn without destroying and to tell what we learn with accuracy and dignity. The Antarctic underworld teaches patience, a message written in clay, glass, salt, and sound that the most consequential stories are often slow to speak but inexorable in the end. As you walk away from this narrative, hold two images in your mind at once: the stark, white, uncomplicated surface that greets your eye, and the complex, watery, singing world beneath it that both records and shapes planetary history. Let those opposing truths sit together. Let them guide policy, inspire cooperation, and feed the public curiosity that will keep this work alive. Keep digging, some secrets still lie just beneath your feet.